Hello everyone. My name is Yutaro Shigeto, a researcher at Chiba Institute of Technology. I'll be introducing our work, learning decorrelated representations efficiently using fast Fourier transform. In this work, we propose a scalable regularizer for feature decorrelation. It is intended as a replacement for those employed in Barlow Twins and VIC-Reg, two latest representation learning models. Their regularizers are effective but do not scale well with high-dimensional embeddings. Our regularizer not only has lower asymptotic time complexity, but also speeds up training by 1.2 to 2.8 times on the ImageNet and ImageNet 100 datasets. Importantly, it also maintains comparable downstream performance. Let's begin by revisiting the Barlow Twins model. From a set of input images, two sets of augmented images are created independently, and a neural encoder network followed by a small projector network generates two sets of d-dimensional embeddings, denoted by A and B. Now, the model's loss function aims to decorrelate features of these embedding. To be precise, a d by d cross-correlation matrix of A and B is computed, and a regularizer in the loss function pushes its off-diagonal elements towards 0. However, calculating the cross-correlation matrix is a computational hurdle when d is large. This is the problem we address in this work. In other words, we are seeking a way to avoid calculating the cross-correlation matrix, while still ensuring feature decorrelation. To this end, we define an efficient regularizer to replace the one appearing in Barlow Twins' loss function. Our regularizer is defined in terms of a d-dimensional summary vector SumVic of the d by d cross-correlation matrix C. Each element of this vector sums d distinct elements of C, as illustrated in this figure for a 3 by 3 matrix. Note: we're using the zero-based indexing. Then, we define our regularizer as the squared norm of the vector excluding the zeroth element, which is the trace of C and is irrelevant to decorrelation. Given that C is still necessary for computing SumVic, this regularizer does not boost efficiency. However, if C is a sample cross-correlation matrix, then we can calculate its SumVic much faster. Indeed, it can be shown that the SumVic of a cross-correlation matrix C can be written like this. This formula suggests that the SumVic of C can be calculated directly from individual embeddings in A and B without computing C. Specifically, we compute the Fourier transform of all embeddings, and simply apply this formula. Its computation time is O of nd log d with FFT, which improves upon O of nd squared, a Barlow Twins' original regularizer. Okay, so we have proposed a fast regularizer to replace the one in Barlow Twins. Here are a couple of notes not detailed in this presentation. First, our regularizer is not as effective on its own, compared with that of the standard Barlow Twins, because ours is in fact a weaker regularizer. However, this weakness can be easily compensated for by feature permutation during training. Second, our regularizer is also applicable to VIC-Reg, another unsupervised representation learning model. Please see our paper or poster if you're interested. We now show some experimental results. These figures show the training time of our regularizer per 10 epochs, across varying embedding dimensionality. On the left, we see the results with the ImageNet dataset in a ResNet 50 backbone, while the right side shows the results with the ImageNet 100 dataset with a ResNet 18 backbone. The orange lines represent when our regularizer is plugged into Barlow Twins' loss. The blue line is for comparison and shows the training time of standard Barlow Twins. The green lines are a variation of our regularizer which we do not talk about in this presentation. As we can see, our regularizer progressively gains advantage as the embedding dimensionality is increased. With ResNet 50, at d equals 8192, it is 1.2 times faster than standard Barlow Twins, and at d equals 10,000, it is 1.3 times faster. With a more lightweight ResNet 18 backbone, speed-up rate is 2.2 at D equals 8,192, and 4 at 16,384. Here is the accuracy of linear evaluation on the ImageNet dataset. Training of the model using our regularizer was 1.2 times faster, but the resulting model performed as well as the standard Barlow twins. Here are conclusions. If you're interested, please visit our poster at the Tuesday morning session. Thank you.